Okay, here's a question for you. What if everything we thought we knew about the universe,
Yeah.
you know, from the tiniest quarks right up to the biggest forces, what if it was all spot on with predictions, but maybe fundamentally wrong about why it all works?
Hmm.
I mean, the standard model of particle physics, it's incredibly precise, right? It lets us build things like the Large Hadron Collider, predict how particles behave with just amazing accuracy.
Absolutely phenomenal accuracy.
But for all that power, it often leaves us asking, well, why? Why does it work like that?
Exactly.
So today, we're doing a deep dive into something pretty groundbreaking, a perspective called motion theory.
Right.
And the key thing here is it's not about, throwing out current physics. Not at all.
Yeah.
It's more about trying to reveal the underlying physical blueprint that makes it all tick.
That's precisely it. The standard model is, well, it's terrifyingly accurate, like you said, at predicting outcomes across all sorts of scales.
Yeah.
From atoms holding together to those huge collider experiments. But the way it does it, it often uses this deeply abstract, sometimes really unintuitive math.
Right. Abstract is a good word for it.
And it doesn't always offer that unifying physical foundation. It describes what happens brilliantly, but it doesn't often give us that intuitive why.
The missing why.
And that's exactly where motion theory aims to step in, to provide maybe a deeper explanation for the why.
Okay, so at its core, motion theory is proposing something, well, it sounds radical, but also kind of elegant.
Mm-hmm.
The idea that everything fundamentally is structured motion synchronizing under constraint.
Structured motion synchronizing, yeah.
And that's not just like a different description. It feels like a whole shift in understanding.
It is.
It suggests that things we call forces, particles, fields, maybe they aren't the fundamental things themselves.
Exactly. They might be descriptions of behavior.
Behavior that arises from this underlying motion, this synchronization.
Precisely. Behavior is emerging from motion dynamics.
Okay, let's try and unpack this. Maybe we can look at some of the big puzzles in physics through this lens.
Sounds good. Where should we start?
How about quark confinement?
Mm-hmm.
That's a cornerstone of the standard model, isn't it?
Definitely.
We know quarks are famously stuck together. The standard model calls it the color force, part of quantum chromodynamics, QCD.
Right.
And the really weird part is that this force actually gets stronger the more you try to pull them apart, like a rubber band snapping back harder the more you stretch it.
Yeah, an unbreakable rubber band almost.
So if everything is motion, how does motion theory look at this? What's this strange pull?
Well, from the motion theory perspective, it's not really a force pulling them together in that classic sense.
Okay.
Quarks are seen as these ultra-compressed, structured motion loops. Think of like a tightly coiled spring, always vibrating, or maybe a perfectly choreographed dance.
The dance, but
Where every dancer, every part of the motion depends on the precise timing of all the others. Their synchronization needs these very specific shared phase states.
right.
So if you try to pull one quark out, isolate it,
Yeah.
it causes what motion theory calls sync collapse.
Sync collapse.
The system just can't maintain that stable rhythm. It needs the full harmonic loop, like the 3 quarks in a proton or neutron, to keep that rhythm stable.
Ah, so it needs the whole ensemble to work.
Exactly. So it's not an attractive force pulling them back. It's more like the structure itself tearing apart because of sync incompatibility when you try to break that essential rhythm.
Wow, okay. That is a mind-bending shift. Less force, more structural integrity failing.
You could put it that way, yeah. The rhythm breaks down.
Which brings us straight to another puzzle, doesn't it? Fractional charge.
Yes.
In the standard model, quarks have these weird fractional charges like plus 23 or negative 13. The math works out perfectly when you combine them.
It does.
But physically, what does it even mean to have a fraction of a fundamental charge? How does motion theory make sense of that?
Well, motion theory suggests these fractional charges aren't static properties. They're actually phase offsets within that motion loop.
Phase offsets, like being out of sync.
Kind of. Imagine different instruments in an orchestra. Each fractional charge represents how much that instrument's rhythm is, let's say, offbeat compared to a perfect full cycle of the whole symphony.
Okay, I like that analogy.
So a quark's charge isn't some inherent thing it has on its own. It's a result of how much its internal motion loop deviates from, well, full cycle resonance.
Right.
And the crucial part is only combinations of these offsets that complete a full two-phase loop, like your plus 23, negative 13, negative 13, adding up to plus 1 charge, only those can synchronize properly.
To form a stable particle we can actually observe.
Exactly. They need to complete the cycle together to be stable. So charge isn't a static piece, it's a dynamic measure of the rhythm's alignment within the whole cycle.
That actually makes the fractional part feel less weird. It's about completing a pattern.
Precisely. It's about harmonic completion.
Okay, that's really helpful.
Yeah.
Now let's get to something that feels even stranger, maybe. Spin 12 particles.
Ah, spin. Always a fun one.
In the standard model, particles like quarks, electrons, they're spin 12. And this quantum number is bizarre because it means the particle has to rotate a full 720 degrees.
2 full rotations.
2 full rotations, yeah, to get back to its original quantum state. And nobody really explains why physically. So what's motion theory's take? Is there a physical reality behind that?
Well, this is where it gets really interesting. Motion theory sees spin 12 as the signature, the hallmark of a bi-loop sync structure.
A bi-loop, like 2 loops.
Essentially, yeah. Think of 2 phase-locked loops nested together perfectly, like a kind of double helix or maybe even a sort of Mobius strip, but made of pure motion.
Okay, a Mobius strip of motion.
And this kind of dual loop structure, it inherently requires 2 full revolutions for the whole synchronization pattern to fully realign with itself.
Oh, so the 720 degrees isn't magic, it's geometry.
It's a geometric requirement, exactly. It arises naturally from that specific bi-loop structure. So spin stops being this abstract quantum number and becomes, well, almost intuitive, a property of the motion's shape.
That's incredible. So this abstract number becomes a tangible, well, geometric reality. Could we, see this structure if we could look closely enough?
In principle, understanding the geometry is seeing the structure. It's about mapping the motion, not just predicting outcomes.
Right, mapping the motion. Okay, moving on slightly, the standard model also leans heavily on these very complex mathematical groups, gauge symmetries, right? SU3, SU2, U1.
That's them, the mathematical backbone.
They describe the allowed ways particles can transform or interact, and they work incredibly well for predictions. But again, they feel quite abstract. Are they just math tools, or is there a physical reason for these symmetries in motion theory?
Motion theory suggests they're not just abstract math rules imposed on reality.
Yep.
Instead, they're seen as emergent behaviors. They describe how these structured motion patterns can reorient themselves without breaking their synchronization.
So how the dance can change direction without falling apart.
Exactly. They arise directly from the physical compatibility of the phase structures. Think of maybe a complex knot. You can twist and turn it, but only in specific ways that don't actually untie the knot.
I see.
The symmetries are the rules of how you can manipulate the knot without destroying it. So the math isn't dictating reality.
It's reflecting it.
Precisely. The math is like a perfect map of the underlying physical rhythms and their constraints, the possibilities inherent in the motion itself.
So the math isn't just a model, it's almost a map of the physical reality of motion. That's a powerful way to think about
It
it.
aims to be, yes.
Okay, what about something like virtual particles and quantum fields? Standard model thinking is particles are excitations in fields we can't see.
Right, ripples in a field.
And these virtual particles are constantly popping in and out of existence during interactions, seemingly from nowhere. If the universe is all motion, how does that work? Where do they pop from?
Well, this raises a really fundamental question. What if there aren't really distinct particles or fields in the way we usually picture them?
Uh-oh. Okay.
Motion theory proposes there are only these motion structures, constantly resolving themselves across gradients, like flows in a fluid.
So no particles, just flows.
Structured flows.
Mm.
And what we call a virtual particle, it might just be a transient phase ripple, a temporary sync disruption.
A ripple.
Imagine a very still pond. A virtual particle is like a momentary flicker on the surface when a fish shifts underneath. It briefly disturbs the pattern, the local sync density, before it settles back down.
So it's not a thing appearing and disappearing.
It's more like a rhythmic disturbance, a fleeting adjustment within the overall motion system, rebalancing things locally, not a physical object popping into existence.
Okay, a temporary blip in the universal rhythm. That actually feels more intuitive than things just appearing from nothing.
It avoids that conceptual leap, yeah.
And speaking of interactions, forces. The standard model uses force carriers, bosons, photons, gluons, W and D particles.
Messenger.
Right, acting like tiny messengers carrying energy or momentum between particles. How does motion theory reframe that? If there's no messenger thing, what's happening?
Yeah, if it's all motion, what's being exchanged, motion theory sees these bosons not as messengers, but more like Sync adjustment nodes?
Sync adjustment nodes.
So a photon, for instance, isn't carrying energy in a packet from A to B. It's more like a temporary rhythmic extension of one structure
Okay.
that's attempting to phase align, to synchronize with another structure.
Like reaching out rhythmically.
Exactly. And gluons, similarly, could be described as sort of phase-bridging elements between the constrained rhythms of quarks inside a hadron.
Bridging the rhythms.
The core idea is there's no physical packet being thrown back and forth. It's all structured motion trying to synchronize or resynchronize with other structured motion.
So interaction isn't throwing a ball, it's like two tuning forks influencing each other's vibrations.
That's a great analogy, actually. It's about rhythmic influence and adjustment.
Okay, that's a big shift too. Finally, let's tackle mass. The standard model gives us the Higgs mechanism. Particles get mass by interacting with this pervasive Higgs field.
The cosmic molasses, some people call it.
Right. But if it's all motion, what is mass in motion theory? Where does stuff come from?
Motion theory offers a profoundly distant perspective here, too. Mass isn't something given to particles by a field.
No.
Instead, mass is motion resistance.
Motion resistance.
It arises from how much the internal motion within a structure needs to compress, or how much it resists changing its phase, its configuration, in order to stay synchronized within the larger system it's part of.
So, like, how tightly wound it is.
Exactly as a tightly wound spring. The more tightly wound, the more compressed its internal motion, the harder it is to push around or change its state. That resistance is what we perceive as its mass.
So more compression, more resistance equals more mass.
That's the idea. More internal complexity or resistance to phase change translates directly to inertia to mass.
And the Higgs field, then? Is it still there?
From this viewpoint, what we've interpreted as the Higgs field might actually be a misunderstanding of a kind of background sync tension, a property of the baseline motion structure of space-time itself.
Wow. Okay. So the more complex or resistant a motion pattern is, the more stuff it seems to be. That's what we measure as mass.
It's a way to frame it, yes. Mass as an emergent property of motion dynamics.
This is quite a reframing of everything.
Yeah.
So pulling it all together, what does this mean for our big picture of reality? Motion theory seems to offer this incredibly unifying vision.
It tries to, yes.
It suggests that every single concept we use in this standard model, charge, mass, spin, fields, particles, all of it, might actually just be our mathematical interpretation of these underlying structured motion behaviors. It's like maybe we were brilliantly describing the ripples and waves on the surface of the water
without fully grasping the underlying currents causing them.
Yeah.
That's a good way to put it.
Yeah.
And again, motion theory doesn't invalidate the standard model's predictions. Its success is undeniable.
Right. It respects the data.
It respects the data, but it tries to reveal the physical skeleton underneath, to provide that intuitive why that often feels missing.
The why.
The really profound shift, if this view holds water, is moving from a universe made of tiny, fundamental things particles swimming in abstract fields to a universe made fundamentally purely of motion.
Just motion.
Structured, synchronized, constantly adapting motion. It suggests a kind of beautiful simplicity underlying all the complexity we observe.
A simplicity born from motion and rhythm. So, welcome maybe to the motion renaissance. If the universe really is fundamentally about motion and synchronization, I mean, what new possibilities does that open up?
That's the big question.
How we understand everything, from the incredibly small to the vastness of the cosmos. What might you, listening now, start to rethink, knowing the universe might be less about static things and much more about dynamic rhythms?
It certainly gives you something to think about.
It definitely does. A universe in constant, structured, rhythmic motion.